Alright, so this video is part of a compilation of videos I've done on Epsilon-Delta proofs, and if you want to see the full compilation, there's a link down in the pinned comments below. But I hope you love this standalone video just to digest this one proof, and I'm excited to bring it to you right now. Alright, so here's our next Epsilon-Delta proof. It's going to be limit x goes to 3 of x plus 2 over x plus 7. So we've got this example, and what I want you to do is actually try it yourself. Okay, try to play around with it yourself and then watch the video just to sort of confirm and see how we're both thinking about it, so you can really consolidate your understanding. So try to sort of work along. The first step, every time I'm going to do the same methodology. The first step is when x approaches 3, when x is exactly 3, you get 5 over 10. Okay, so we're going to get a half. Okay, 5 over 10 is a half. This is a continuous function. Now I just want to make a comment is, suppose you were trying to do an epsilon delta proof where it was an indeterminate form, okay, like 0 over 0. Usually with those examples, what you do is you simplify the function. So as an example, I could sort of write this down. You know, if you had something like limit x goes to 1 of x squared minus 1 by x minus 1, right? Then you couldn't actually plug in your x equals 1, right? You wouldn't get an expression. You get 0 over 0 if you plugged in x equals 1. But the same principles would apply. You basically want to, you know that this quantity, when you deal with these, you know this quantity is just equal to x plus 1 when x is not equal to 1. Okay, so as long as x is not equal to 1, then you know this quantity is x plus 1. And so then you can basically do the same argument as if you had x plus 1, because they are the same expression. And that's how you do limits when they're 0 over 0 forms. If you're not using L'Hopital's rule, if you're using that, then already you've gone through all the work with epsilon delta secretly. But in this case, you know, if you're just simplifying, you know this expression is true. All right, so let's get into this limit now. So basically what we want to do, it's the same game. We want this expression x plus 2 divided by x plus 7. Absolute value is a distance as usual. So we want this minus a half to be less than epsilon. Okay, so we want to ensure that this expression is less than epsilon as long as x is sufficiently close to 3. Okay, so how close to 3, that's what we have to find out. We want to say that for each epsilon I pick, if I want x plus 2 over x plus 7 minus half to be that small, the absolute value to be that small that it's less than epsilon, then you're going to tell me a delta. So as long as x minus 3's absolute value is less than delta, i.e. x is sufficiently close to 3, then x plus 2 over x plus 7 is sufficiently close to half. So we want to find delta in terms of epsilon. It's the same game. So again, as always, we simplify the expression here and try to write it in terms of x minus 3. Okay, so we try to write it in terms of x minus 3. Well, let's just get into it. So here we have x plus 2. Just make a common denominator. That's what I do. So x plus 2 multiply by 2. So we get 2 times x plus 2 divided by x plus 7 minus x plus 7 divided by 2 times x plus 7. Okay, so I should say 2 times x plus 7 and 2 times x plus 7 here. And I want this to be less than epsilon. Okay, so that's my expression. And so in this situation, you know, I just simplify what's inside this absolute value. So I'm going to do it on this side of the board now. So we're just going to get 2x plus 4 minus x plus 7, which is going to be the absolute value of x minus 3 divided by 2 times x plus 7. Okay, so that's going to be our expression. And we want to say that this is less than epsilon. Okay. Now we see the absolute value x minus 3, which we should see. Okay, we know this expression should be 0 when x is 3. Okay, that's because we're dealing with a continuous function that is defined at 3, and the value at 3 is the limit as x goes to 3. So that's what we intuitively know. We're creating a proof based on our intuition. So now we know that we're going to see an x minus 3 if we simplify it right. We've seen that. Now we need to pick our delta. So how are we going to do that? Well, again, okay, so we have this extra expression like we did last time. So we can separate this into 2 pieces. Okay, we have our absolute value x minus 3, and then we have our 1 over 2 times x plus 7. Okay, again in absolute value, we want this to be less than epsilon. Now, again, you know, it helps. It's not rigorously true, but it helps to say that if x minus 3, okay, if absolute value x minus 3 is going to be less than epsilon times the absolute value of 2 times x plus 7, okay, if this is true, if we know that, then we can ensure that this quantity is going to be less than epsilon, right? So if we take delta to be this, then we've solved the problem, but we can't do that because this is dependent on x, and we want delta to be only dependent on epsilon. So how do we pick our delta? So again, we think about the extremes, okay? So we pick what is x plus 7 going to be when x is 3. When x is 3, x plus 7 is going to be 10, and this is going to be 2 times 10, which is 20. Okay, but But then of course we know that, we want our delta to be equal to epsilon times 20. Okay, that's actually like a different sense as earlier. It's not epsilon over something, it's 20 epsilon. But that's not enough, because now if x is, within some units of 3, right? So for example, if you have 3 on the number line, and I can even write it here. If you have 3 on the number line, and your x is going to be like, say, between 2 and 4. It doesn't matter what I pick. Okay? I'm just picking 2 and 4. It does matter as long as the denominator is non-zero. Okay, so I have to pick it in the domain, some interval in the domain. But if I say that x is between 2 and 4, then when x is exactly 4, I want my absolute value x minus 3. When x is approaching 4, I want my 2x plus 7 to be, it's going to be 22, right? 22. So our delta needs to only be 22 epsilon. But when our x is approaching 2, our 2x plus 7 is going to be 2 times 9, which is 18. Okay, so we're going to get an 18 epsilon here. So remember, we want to pick the delta that's optimal no matter what situation we have. Okay, so at 3 exactly, we have 20 epsilon. So the safest thing to do is to pick delta to be the minimum of 1, okay, because I've looked at the range from 2 to 4, and 18 epsilon. And then no matter what x is in this range, 18 epsilon is going to take care of everything in this range, because all the other required deltas or required values of the 2x plus 7 in that range are going to be higher, okay, than when it's at exactly 2. Okay, so again, I'll write out the proof. I hope that everything is so far very clear. I'll write out the proof now and really make that precise. So let's do that. All right, so let's write out the proof. So how these proofs go is always the same. Let epsilon greater than 0 be arbitrary, so it doesn't matter what epsilon is. Our goal is to pick a delta so that if the absolute value of x minus 3 is less than delta, then the absolute value of x plus 2 over x plus 7 minus half is less than epsilon. So let's just get into it. It's super fun. So let delta equal to the minimum. So I'm going to write this again. Let delta equal to the minimum of 1 comma, in this case 1 comma 18 epsilon. Okay, so actually you could just say, and this is another point in these proofs, we don't have to pick the optimal delta. Okay, you can say let delta be the minimum of 1 comma epsilon. That would be even better. Okay, that would make it easier. That's fine. But the main thing is it's nice, it's just like an aesthetics, like an artistic thing. It's like people like to do it this way, but you don't have to. As long as you say the end expression is less than epsilon that you want, it doesn't matter what delta you pick. Okay, so if we know it's less than epsilon over 18, then that's also less than epsilon. So that's totally fine. The only thing we want to be careful about, and I'm just saying this before I get into the proof, is we don't want to in the end say it's less than some expression in epsilon that is not less than epsilon. We don't want our proof to read as if absolute value x minus 3 is less than delta, then this expression, the absolute value of this expression is less than, say, 5 epsilon squared plus 7 epsilon plus 2 or something, or 5 epsilon squared plus 7 epsilon. Now, technically, I'll talk about this a bit more, but technically that expression, if we can say it's less than 5 epsilon squared plus 7 epsilon, that's technically okay, because that expression tends to 0 as epsilon tends to 0. Okay, so, but it's important that we, to be very rigorous, we want our end expression to be less than epsilon, because we're saying that's our exact degree of specificity and we're making it within that range. Okay, if we say it's 5 epsilon squared plus 7 epsilon, advanced math papers, they do that. Okay, and that's fine. They can say it's some constant times epsilon, and that's fine. That solves the problem. They don't bother to go and say let delta be whatever it was divided by that constant. Okay, but we are just being very precise because this is like the first steps in these proofs to make sure our rigor is correct. So anyway, let's get into this. So let delta equal to this minimum of 1 and 18 epsilon. And now what we can do is we can say, all right, so if the absolute value of x minus 3 is less than delta, then we know, and I'm going to do it slightly differently as I did earlier. I'm going to say, then we know that the absolute value, so whatever expression we had earlier, the absolute value of x plus 2 divided by x plus 7 minus half, what's that going to be? That's going to equal to, after all our simplifications, that was x minus 3 divided by 2 times x plus 7. Okay, so we know that this is going to be less than, well, delta was the minimum of 1 and 18 epsilon. Okay, so it's the smaller of the two, whatever that is. Okay, so it's less than or equal to both of them. So because it's less than 18 epsilon, we can say the absolute value of x minus 3 is less than 18 epsilon, and then divided by 2 times the absolute value of x plus 7. Absolute value of 2 is 2, so I just took that out. Okay, it doesn't really matter. But now the point is that because delta is a minimum of 1 and 18 epsilon, so using the 1, we know that the 2x plus 7, x plus 7 is going to be the smallest value x plus 7 could be, right? Because x is within 1 of 3, okay? Because delta was a minimum of 1 and 18 epsilon. So the smallest value that x plus 2 times x plus 7 could be is actually 18, okay? Because if x is 2, right? X is within 1 of 3. So if x is 2, then you get 2 plus 7 is 9. 9 times 2 is 18. Okay, so this is going to, the denominator is greater than 18. So that means if you take the reciprocal, you get a less than sign. It's going to be less than 18 epsilon by 18, which is going to equal to epsilon. Okay, so we've chosen our arbitrary epsilon. We found a delta, which is a minimum of 1 and 18 epsilon. And notice we've been very careful to say minimum of 1 and 18 epsilon. Okay, so we've used both the fact it's smaller than or equal to 1 and smaller than or equal to 18 epsilon. And again, you could have chosen it to be the minimum of 2, comma, then you'd have to say it was 16 epsilon. Okay, so if it was 2, then x could be 1, and then you'd have 16 as the minimum value of 2 times x plus 7 in the range of 1 to 5. Okay, so if you took the minimum of 2, then your x would be in the range of 1 to 5. Okay, so that's there. So let's, now that we've done that, please feel free to drop any questions or comments down below. I love reading comments. I do my best to reply to everyone, and I really value everyone who watches and enjoys my videos and learns from them. It means so much to me. So we're now going to get to the next limit now, and this is going to be another one which is really, really fun. It's going to keep practicing with this idea that we've already seen a couple of times. But then the final limit, that's going to be slightly different, okay? So I'm just training you to think in all different kinds of situations, but I'm also showing you that it's the same scenario each time essentially. It's just the numbers and variables are changed.